So, hey everybody, I'd like to welcome Isaiah Andrews and Jesse Shapiro, and they're going to be talking about a paper with Matthew Genskow. And the real motivation for inviting them here and informing us is that a lot of what we do in Alphabet Modelers is automating science, and kind of implicitly this is what we're doing. And what this work is starting to do is trying to build the theoretical foundations behind philosophy of science. This is kind of my interpretation of it. And actually capture what scientists do or should be doing in order to communicate effectively among each other. So welcome and thank you for coming.
Fantastic. Thank you. Thank you so much for the invitation to come, and really excited to be here. Really looking forward to getting folks' comments. So the topic we're presenting on is transparency and communication in scientific research, and this is based on a number of joint papers with Matt Genskow and Jesse Shapiro, and Jesse is here. So again, thank you so much for having us. So the point of departure for this line of work is a classical model of statistics dating back to Wald. So in this model, we'll think of an analyst who observes data X and is interested in using that data to form an estimate of an unknown parameter, say theta, where we'll think of that estimate as being good if it's close to the true value of the parameter. Right? And the usual formalization for this is to imagine estimation as a decision problem, where the estimate is some decision, say little d, in a set of possible decisions, script d, and we're picking that decision to minimize a loss that depends on the decision and the true value of the unknown parameter theta. Right, in this basic setup, thinking about estimation as a decision problem is the dominant paradigm for optimal point estimation, forecasting, and so on. Right, for example, if we think of LD theta as just being the square difference between d and theta, this gives us the canonical mean squared error criterion, which is very familiar from both point estimation and forecasting settings. If we sort of take that model and put it in a picture, right, it could look like this. Right, so we've got a data generating process that gives rise to data that goes to an analyst. That analyst then uses the data to form an estimate or a decision, which in turn determines a loss. Right, we think that this classical model seems like a pretty good description for certain types of real world settings. Right, think, for example, of an analyst who works at a firm that must make a pricing decision. At the end of the day, the price that the firm sets is what determines the loss or profit or utility, and this model, at least at a sufficient level of abstraction, seems like a reasonable description of the problem. In this project, though, we're interested in thinking about another possible model here, where you've got a data generating process that again gives rise to data that goes to an analyst. But the analyst then uses those data to form a report, which goes out to an audience, where different members of that audience then use the information contained in the analyst report to form their own estimates or decisions. And it's those estimates or decisions made by the audience which ultimately matter for the loss. Right? We think that this alternative model seems like a better description for certain types of scientific settings. Think, for example, of an analyst who's reporting their results to scientists with diverse opinions or policymakers with diverse objectives. Right? In both of these cases, different members of the audience might take different actions on the basis of the information in the analyst's report. And it's those actions taken by the audience members which ultimately matter for loss, utility, social welfare, et cetera, not per se the report that the analyst makes. So have set up these two different models. One reasonable question is whether the distinction actually makes a difference. And what I'll start by arguing today is that these two different models represent fundamentally different and at times actually quite conflicting views of the goals of a scientific analyst's goal. Once I've done that, I'll then talk about some implications for practice with applications to empirical research in economics. So the results I'll talk about today are based on a line of joint work with Jesse Shapiro and Matt Genskow. So 3 of the papers are joint with Matt, all of them are joint with Jesse. And as you might expect, given that I'll be drawing on material from 4 papers for today's talk, I'll be glossing over a lot of details, but if you're interested in the gory details, they are all available in the papers, and I'm also, of course, happy to talk about them. So before I jump into talking about these contrasting models in more detail, let me pause here to see if there are any questions.
Well, so I have a question just about the motivations. Why reports? Why they just broadcast the data to everybody? I mean, just this model.
Absolutely, absolutely, yeah. And I think in some sense, I think the practical reason we are I think our view is that in practice, right, just the way that we do scientific communication strongly suggests that we are subject to various communication or data processing constraints, right? It's in a lot of these settings, it's clearly not like a pure communication constraint in the sense that for many empirical settings, researchers could just post the data on their website. It's not impossible to transmit the data. There's not some sort of a privacy reason they couldn't post it. But nonetheless, I sometimes feel like I learn a great deal from reading empirical papers, even on data sets which are publicly available. And so in some sense, we, at least at this stage, don't feel like we have a perfect model for what are those communication or data processing constraints. And so the way we are approaching that so far is to say, let's say that the goal is communication, and we can certainly think about trade-offs across limited sets of rules, right? But if you wanted to say, what's the unconstrained optimal communication thing? Well, then you would have to take a stand on, what is the communication constraint, right? At the moment,
that makes sense.
Yeah, we've modeled that in some simple ways, right? We have some results for discrete settings, things like that. But I think the question of fundamentally, why is it that if someone just posts a data, what is the right way to model the reason why if someone just posts a data file on their website, I find that less helpful than reading the paper, I think is a really interesting and important question, but not one that I think we at least feel like we have a great answer for, right, even though we're confident it's true.
Yes, it would be more like behavioral psychology at that point, or something like that. Here's if you do that, then here's what you should watch out for.
Exactly, yeah. And in some sense, I would say, I think the as you'll see, the comparisons I feel like we're pretty comfortable making are here are two rules, or here's a set of rules, all of which are clearly feasible to report because people do report things like them, and I feel like we understand them, and we can think about the trade-offs among those. But if you want what's the unconstrained optimum among all things you could do, then you need to say really what are the constraints we're facing. And in some simple cases, I feel like we have some intuitions, but in the general case, exactly like you're saying, that's a important psychology question that we at least don't feel like we know the answer to.
It makes sense.
Thanks so much for the question. Excellent. So with that, let me dive into fleshing out these contrasting models we've got in mind in a bit more detail. So let me start with the timing. So the model we have in mind here is one where the analyst is first going to publicly commit to a rule, where a rule is just a mapping from possible data realizations to possible decisions or reports. The analyst is then going to observe the data X, where the distribution of X is governed by the unknown parameter theta. The analyst then makes a report C of X to an audience of agents. So they just apply their pre-specified rule to the realized data and report that out to the audience. Each agent little a in the audience script A sees the information in that report and then selects their own decision and realizes a loss, which depends on their decision, and the true value of theta. Now, agents in the audience are going to differ in their priors on the parameter theta. So we'll write expectation subscripted by A to denote the expectation taken under agent A's prior. For simplicity, we'll be assuming that the only way in which agents differ is in their priors. So we can just identify each agent with their prior and take the audience to be a subset of the set of possible beliefs on theta. Something I should note is if you prefer to think about settings where agents differ in their loss functions or differ in their loss functions and priors, you can embed that in a setting where they differ just in their prior by redefining the parameter space appropriately, which is something we talk about in the appendix of the paper. So it's without loss in some sense to think about this setting where all the heterogeneity lives in the prior. Now, to keep life simple, we're going to think about a case where the analyst here is benevolent. And the goal of the analyst is just to help the agents minimize the expected loss, or in decision theory jargon, the risk. But to make that precise, we need to define what notion of expected loss or risk we're using, and we'll think about two. So the first, which we'll call decision risk, is the usual notion of risk from the classical model of statistics that I started out with. So here, right, the expected loss of a rule C for an agent A, right, which we'll write like this, is just the expected loss from plugging the rule C into the loss function evaluated under agent A's prior. Right, so you could basically think of this as what's the expected loss under agent A's prior if the analyst is making the decision on the agent's behalf. The second notion of risk we'll use is what we'll call communication risk, and this will correspond to that alternative model for scientific communication that I introduced. Okay, we'll put a star superscript on that to distinguish it from decision risk. And here, what's going to happen is each agent is going to see the analyst's report, form their posterior belief on theta, given the information contained in the report, then choose their action to minimize the expected loss with respect to that posterior. And then the communication risk is the ex-ante expectation of that minimized object. Right, so you can think of this as basically the ex-ante expected loss under agent A's prior if the agent knows that they're going to take the optimal action based on the information contained in the analyst's report. Now, the distinction between these two notions of risk is going to be irrelevant if the audience contains just a single belief, right? Because we've assumed that the analyst is benevolent, and so if there's just one belief in the audience, what a benevolent analyst can do is just recommend the optimal action for that agent. However, the distinction between these two notions of risk can matter a great deal when there's more than a single agent. So to illustrate that and the distinction between these two notions of risk, I want to talk through an example. So think about an analyst who is conducting a randomized trial with a binary outcome, where the goal is to learn the success probabilities, theta 1 up to theta j, at each of a finite set of ordered treatments 1 to j. For example, you could think of a demand estimation setting where I'm thinking about offering a given product to a randomly selected consumer at a set of j different prices. Right, and theta 1 up to theta j are just the probabilities that a randomly selected consumer purchases the product when it's offered at price 1 up to price j. Alternatively, you could think of a labor economics example, right, where I'm generating artificial resumes, and I'm thinking about the effect of unemployment duration on callback rates. So the j different treatments are I'm reporting being unemployed for 1 week or 2 weeks or 3 weeks or 4 weeks, etc. And the theta j's are what's the probability that a firm is going to make a callback offer to a resume which reports being unemployed for 1 week, 2 week, 3 week, 4 weeks, etc. And for this example, let's further suppose that we know ex ante and all agree that the success probabilities are decreasing. So theta 1 is greater than or equal to theta 2, greater than or equal to theta j. Right, so in the demand estimation example, this would say demand curves slope down. Right, so if I offer the product at a higher price, folks are less likely to buy it. Or in the unemployment example, this would say that longer unemployment spells deter employers. Finally, let's think about quadratic loss again, right? So where since theta is now a vector, this is just going to be the sum of the squared estimation errors over the components of theta. Now, let's suppose we've got n independent observations for each treatment, and let the data X consist of just the fraction of successes for each, right? So the fraction of resumes that get a callback for unemployment duration 1 to up to j. Let's just take the decision space to equal the sample space, which says that the analyst is free to just report the full data in this setting if they want to. And let's take the audience here to consist of the set of all possible priors on theta. Because I've put this restriction, right, that theta is decreasing in j on the parameter space, that's going to mean that everyone agrees with that restriction, right? Everyone thinks the true theta is weakly decreasing in j, but folks potentially disagree about everything else. So to get started in this setting and actually coming back a bit to the discussion I was having with Greg at the beginning, imagine an analyst who's just choosing between two possible rules in this setting. So the first rule is just going to be the full data rule, right? So the jth element of the full data report just reports the success fraction for the jth treatment. So this is just the rule where the analyst takes the data from the experiment, reports it out to the audience, doesn't do anything else. Second, let's think about what we'll call the rearranged data rule. So here, right, the jth element of the report is going to correspond to the jth highest element of x1 up to xj. Right, so the idea here is I'm going to take the success probabilities for the j treatments, sort them in descending order, and then report out that sorted list without reporting which of those sorted elements originally corresponded to which treatment. So to visualize this, right, imagine that I run an experiment and this is the outcome, right? So I've got unemployment spell duration on the horizontal axis, callback rate on the vertical axis, and we see in the experiment that the callback rates are generally decreasing, although not perfectly monotone, right? It increases in these two places. So the full data rule would just report out this experimental result. By contrast, right, the rearranged data rule would take this, sort it in descending order, and then report out this sorted picture without telling us, which of these points originally corresponded to which treatment. Now, if we think about this setting from the perspective of, I'm trying to report something that's as close as possible to the truth, there's a sense in which just reporting the raw data here is unreasonable. Because remember, we all agreed that the truth here is weakly decreasing. So we know that this can't possibly be the truth because it's not monotonic. By contrast, this sorted report could potentially be the truth because it is at least monotone. And indeed, you can formalize that and show that reporting the rearranged data in this setting dominates reporting out the full data in decision risk, meaning that it achieves weakly lower risk for all agents and strictly lower risks for some. Intuitively, basically what's happening here is in settings with a monotonicity restriction like this, you can show that enforcing that restriction by reordering is guaranteed to get you weakly closer to the true parameter all the time, strictly closer some of the time. And so this is a better thing to report if my goal is to report something close to the truth. And correspondingly, the classical model would recommend reporting the sorted data over the raw data. At the same time, from the perspective of communication, there's something that seems weird about that recommendation. In particular, the sorted data rule maps this realization of the data to this report, but it also maps this realization of the data to the same report. And it maps this third realization of the data, again, to the same report. Now, at least for me, even if I am certain ex ante that the truth data is weakly decreasing, right, these three data realizations would leave me with a quite different posterior belief on how steeply decreasing the relationship is, right? I have a much steeper belief in this case than I would in this case.
And I want to clarify something.
Yep.
You're saying not just all agents share this belief about decreasing, it's that reality is in fact like that. They're in fact, the loss function will support their belief.
Yeah, I guess the way I would say it, in some sense, right? So we are going to be assessing everything with respect to the class of beliefs in the audience. So if everyone in the audience believes with certainty that something is true, that sort of is all that actually matters for us. But yeah, imagine in this case, the truth is in fact strictly decreasing. So there's not an issue of like the agent beliefs are mistaken or anything like that.
Okay. Makes sense.
So in this setting, right, these three data realizations would leave me at least with a quite different posterior belief. And that's information that's lost if all that I get is the sorted list, right? Because if all that I get is the sorted report, I don't know which of these three actually occurred. And again, you can formalize that in our setting, right? And show that reporting the full data, right? Basically disaggregating these three cases dominates just reporting the rearranged data in communication risk. Right, essentially, if I'm just giving the sorted list, that loses decision-relevant information. In particular, how steep my posterior would have been if I'd observed the underlying data in these three cases. And indeed, the issue here is broader than just the comparison between those two particular rules. So we're going to say that a rule is admissible in a given notion of risk if it's not dominated by another rule. And in this particular example that I've set up here, you can show that any rule which is admissible in decision risk is inadmissible in communication risk and vice versa. Right, so in a strong sense, there is no rule which resolves the conflict between the two notions of risk in this example. Right, so any undominated decision rule, in this example you can prove necessarily discards useful information. Well, any admissible communication rule necessarily sometimes recommends bad decisions, right? And so in this example, if I say my goal is to communicate useful information to the audience versus if I say my goal is to report something as close as possible to the truth, those are going to drive me to fundamentally different recommendations in this case. And actually, coming back to the question you raised a little earlier, Greg, on sort of reporting the full data, et cetera, in this example, you are actually free to report the full data. And it just turns out that the sort of classical model with the monotonicity restriction would actually say you don't want to report the full data unless the full data gives you something monotone, which even if the truth is monotone, sometimes by chance you'll get a non-monotone data realization. So that generates the issue. And indeed, it turns out that this conflict between the goal of decision and the goal of communication is broader than just this one example. So in the project, we provide sufficient conditions for admissibility conflicts of this sort to arise in a range of cases which nest the example. And the existence of such examples to us highlights that the goals of decision and communication can really be in conflict. And so that the recommendations of the classical model, right, which say that, my goal is to report something as close as possible to the truth, say, may not actually achieve the goals of a scientific analyst who's trying to communicate information to the audience. So solving the decision problem may mean that I'm actually not solving the communication problem, and vice versa. So before I move on, let me pause here for any questions.
So I'm not sure if you're going to get to this again, but the definitions of decision risk versus communication risk.
Yes.
I think given the example, I think those are suddenly making more sense. But if you can go over them, I think now it's actually, the formalism might be more intuitive.
For sure, yeah, absolutely. So decision risk is basically just saying, so the decision risk of a rule C for an agent A is just saying, if I plug the rule C into the loss function, what's the expected loss under agent A's prior? Right, so in the example, right, decision risk would basically just be the expected squared estimation error from a given rule, right, under a given agent's prior.
So it's a prediction risk.
Exactly.
It's what the standard statistical model would have thought of as error.
Yeah, exactly. So this is just the standard. This is like the standard plain vanilla optimality criterion that shows up in point estimation, shows up in prediction. Just mean squared error, squared estimation error, squared prediction error. Plain vanilla. Mm-hmm. And then the communication risk is the one that's different. So the communication risk, right? What I'm going to do is I'm going to say for each agent A, they're going to see the analyst's report. They're going to form their own belief about theta given the analyst report, right? So basically, I'm going to Bayes update based on seeing the analyst report. I'm then going to minimize my posterior expected risk, right? So given the information in the analyst report, I'm going to do the thing that's the best thing to do under my new posterior. And then the communication risk is the ex ante expectation of that object, right? So this is basically saying, before I see the data, knowing that the analyst is, using a particular rule and that I'm going to take the optimal action in light of that rule, how big do I think my squared estimation error is going to be? Right? And so then when we think about this example, right, so let's go through the two cases here actually. So first for decision, right, going with the sorted report is better than reporting the raw data for decision, because you can basically show that enforcing monotonicity in this way is guaranteed to get you closer to the truth. And so if my goal is to get close to the truth, I should enforce monotonicity. For communication, right, the issue is that the reason why sorting the data gives me a higher communication risk, right, is exactly that basically I lose the ability to distinguish between these three cases, right? And there are some beliefs in the audience where these three cases would lead that audience member to make a different decision, right? So in this case, maybe I choose a sort of shallower curve than I do in this case. And if all that you give me is the sorted report, right, well then I sort of can't undo that sorting and back out the decision I would have made if you'd given me the raw data.
Okay, so I think this is really the core of the approach, because it's trying to capture something about the social practice of science in this formalism.
Yes.
So it sounds like the intuition for how you're trying to capture this is there's a computational procedure that, given the report the analyst does, which you're not putting computational bounds on it. It could be like any Turing complete algorithm kind of thing.
Yeah.
And I'm assuming getting the full data is always the best thing because that procedure can do anything with the data.
Exactly. So sort of if we, right, so the one thing that is going on in the background here, right, is there's the, right, we're sort of saying that the analyst's report has to live in this set script D, right? And so in principle, you could constrain the cardinality of D so that it's smaller than the cardinality of the sample space, in which case you can't report the full data. But in this example, we're setting D equal to the sample space, so you're free to report the full data. And from a communication perspective, as we've set up the formalism, if you can report the full data, that's the best, that's always the best thing to do for communication, because exactly like you're saying, then the members of the audience can do whatever they want with that report.
Okay, but it's not just whatever they want, because you didn't just say there's a unknown function f of c of x, and you want to get that function f as accurate as possible, because then always full report would be way better than everything else and probably wouldn't be informative. You said you're using this loss and trying to minimize over the loss, like maybe the formulas, maybe next slide. So what are you trying to capture by this expected value of the minimum expected values of losses? What scientific process are you trying to model here?
Yeah, so so if we took the decision space D to be continuous, right? So imagine that instead of the decisions living in a discrete space, imagine we take the decisions to just live in RK, right? K-dimensional reals, and you did squared error loss for the loss. This object is actually just the expected posterior variance for agent A. Right, because basically the optimal decision in light of the information in the analyst report for squared error loss is the posterior mean. And so basically in that setting, what communication risk says is I want to report the stuff to the agents in the audience that helps reduce that gives them the smallest possible posterior variance. And so in that sense, reduces their uncertainty as much as possible.
Okay, and then what I think is maybe missing from this formalism that I'm not seeing is the connection between theta and C, because there's some model of arbitrary complexity right now that some internal parameter of that thing is theta, and you tune that theta based on C of x. That could be anything.
So the way I would think about, I'd flip it. So I'd say, right, so theta is sort of the state of the world, right? Theta is the underlying data generating process. It's sort of the thing that's out there in the world. And then the analyst is picking C. Right, where basically the analyst's goal in picking C is to minimize, one of these notions of expected loss. And C here is just some mapping from the set of possible data realizations to the set of possible reports. Right, and so it's basically of all things all functions in the data I could possibly report, which is going to be the best to report to the audience for minimizing the expected loss in one of these senses.
Cool. No, it's making sense. And just, what did you want to add?
I just wanted to jump in and say, like, another way to think about it that could be helpful. You guys can hear me, right? Yeah. Another way to think about this that could be helpful is, like in both cases, decision risk and communication risk, it's the analyst who chooses the rule that maps from X to C, from the data to what's in the report. But the difference, one way to think about the difference, or a different way to represent it, is in the case of decision risk, the rule that maps from the report to the decision is also fixed, and it is just like the identity rule that just says the decision is the report. But in the case of communication risk, you could imagine that what's going on, it would be equivalent to this, is that the agents specify their own rules in advance. They say, here's a rule that's going to map from the report to my decision, and they're just going to optimize that rule with respect to their prior beliefs. That would be equivalent to the formulation here. This is just, here we're representing the timing differently, but because there's, everybody's Bayesian, it doesn't really matter how you think about it. So here we're saying you get a report, you update your beliefs, you choose your optimal decision. Another way to think about it would be you just pick a rule, a machine that's going to map from whatever the scientist reports to what you're going to conclude or what you're going to do. And then the scientist executes their rule and you execute your rule. And that would be equivalent to this notion of communication risk. Does that make sense?
That's helping. And now, I mean,
and we're not imposing any constraints here on the shape or form of that second rule. That mapping from the report to the decision could be anything.
Okay, so now let me bring you to a different domain, which is now a lot more common here, which is this smells a lot like an embedding function, when you have like a neural net, you embed a giant parameter space, cat videos into like the boundaries or whatever, higher level attributes of the cat videos. That's a report as far as I can tell. So I'm trying to figure out what does this say about the and afterwards you're going to be doing a lot of stuff. You can say cat, dog. You can actually use that embedding. I mean, it's really common to create embeddings of a bunch of stuff, then use them for other stuff because they just have nice properties. Similar things are similar in that embedding. Mm-hmm. So that's a lot like a report. I don't know. Have you thought about how your model maps to neural nets?
So definitely I've not thought about how it maps to neural nets, but I do agree there is a definite similarity to the setting you sort of lay out, in the sense of, right, the sort of decision risk setup is basically saying, what I'm going to evaluate is how good is that first step embedding on its own, right? And just like I'm going to come up with some criterion for just saying, how close does that get to some ideal that I want in some sense. Whereas the communication setup is basically saying, so I've got that first step embedding, but how I'm going to evaluate it is then there's some family of second step analyses I'm going to be doing based on the first step. And I'm going to evaluate the first step based on how good a second step do they allow, right? Which I think comes to this.
Yeah, this actually makes me curious about like that next, one of the downstream applications of this is I'm going to compute an embedding that's useful for a bunch of stuff.
Yeah.
How do I evaluate different choices for embeddings?
Yeah, and I can tell you sort of, so I'll tell one of the next results I'll get to will speak a tiny bit to one aspect of this. But yes, I totally agree. Yeah. And Jesse, also, please, thanks for jumping in. Please do jump in.
I'll add also that, like, from the standpoint of thinking about that kind of situation, the alternative representation of the model that Isaiah mentioned briefly, in which the disagreement among the agents is not in the prior but in the loss function, mm-hmm. is also helpful, because there's a sense in which that's kind of equivalent. And basically in that version, everybody maybe has the same beliefs, but they just have a different thing they need to accomplish. So some people have one loss function and some people have another. You could even have different decision spaces and stuff like that. Ultimately, what's important is that in this communication risk case, the analyst needs to worry about many different possible ways the same report can be used. Whereas in the decision risk case, there's really only one.
Yeah, and I'm thinking also transfer learning, where it really is different models of the world because you're using an embedding for training one data set for a bunch of others, and reality is in fact different there, as well as applications.
Yeah.
And actually, one thing I'm noticing is here you do have a notion of why you want to make a report. You don't want to retrain the embedding every single time. Mm-hmm. And you cannot afford to provide all the data. It is, many petabytes of, like, think of all the language models. Petabytes of data, or probably more than that. Do not want to communicate them out. Want to train like the giant language models they have once, and then keep reusing them.
Yeah.
Right. It's interesting. Cool. Yeah, like this is actually the motivation here. We're trying to automate scientists. So now we have computational notions of costs and the motivations. Nice.
Yeah. That's super interesting. Yeah, we had not thought about that connection, but that is super interesting. Thank you.
Yeah, awesome.
So actually, coming to that, related to this discussion, next thing I want to talk about is some other optimality criteria we could think about here. So for that example I started with, I was focused on admissibility, right? So undominatedness. But admissibility is rarely the focus in applications. Right, after all, the class of things that are undominated by something else is usually really, really big and contains lots of unreasonable procedures. Right, and so it doesn't provide a unique recommendation. So we might instead think about other criteria that do provide unique recommendations. Two such criteria that see a lot of use in practice are weighted average risk and maximum risk. So weighted average risk, basically what we'll do is we'll specify some weights omega over the audience, right? And then calculate the weighted average of the risk with respect to omega, right? So basically I'm going to say, I care this much about performance in this case, this much about performance for that audience member, this much about performance for that audience member, and so on. And minimizing that weighted average leads to Bayes decision rules in the classical model, right? So you can think of this as the criterion which justifies Bayes in our setup. Alternatively, you could think about maximum risk. Right, so choosing weights omega is hard, and so maybe what I'm going to do is I'm actually just going to focus on the worst case risk over the audience A. right? And if we minimize the maximum risk in the classical model, that leads us to minimax decision rules. So let's think about the implication, sort of the distinction between these two notions of risk for these two optimality criteria. So first, for weighted average risk, we get another negative result. So in particular, suppose we limit attention to weights omega with support A, right? So basically weights that are supported on the full audience. In that setting, you can show that if there's an admissibility conflict, like in the example we started with, decision optimal rules are not going to be communication optimal for any choice of weights and vice versa. Right, and so in that sense, we're again in this world where saying my goal is optimal communication and my goal is optimal decision-making just points in very, very different directions, even if I'm allowed to attach different weights to over audience members for the communication and the decision-making cases. And one implication of that is that in settings with an admissibility conflict, Bayes' decision rules are dominated for communication. Right, where the intuition here is basically that with a heterogeneous audience, it's actually not helpful to bake in a particular prior. Right, and instead what we want to do is convey some information about what's going on in the data and let the audience update. Interestingly, for minimax, we actually get a positive result. Right, so if the audience A is convex, right, basically meaning if I take two beliefs in the audience, there's a third belief in the middle, then minimax decision rules are minimax communication rules, in the sense that if I have a rule C star, which minimizes the worst case decision risk over the audience, it also minimizes the worst case communication risk over the audience. Right, and so this says that if I only care about the worst case performance, it actually suffices to report a minimax decision rule. Now, one caveat I want to flag here is that this result does not actually overturn our earlier negative results. Right, and the reason why is that minimax sort of worst case performance, right? I can have something that's minimax, sort of does as well as possible in terms of worst case performance, but is dominated, right? Underperforms on some part of the space, right? And basically that's how these two results can coexist. And this was actually the result I had in mind following up on your earlier, on your last question, Greg, because I think if I'm thinking about the relationship between the settings here, right, I think what this would say is that, imagine we could use the loss function formulation Jesse introduced. So imagine I've got some, I'm doing a first stage, I'm doing some sort of a first stage analysis. I'm then going to pass the output of that to a bunch of second stage purpose, right? That's going to be used for a bunch of second stage purposes. So in that context, right, subject to our regularity conditions, what this result says is that basically picking the first step output that does as well as possible, the first stage procedure that does as well as possible in terms of its worst case performance over those different cases in the second step, that actually optimizes sort of basically that. Picking the one stage procedure that does as well as possible in terms of worst case performance over those second step things, optimizes basically the worst case performance I will achieve in the two-step thing, is basically what this minimax result is saying. So with that, before I move on to the last section, let me pause for any other questions. Cool. Excellent. So last, let me talk a little bit about implications for empirical research. So in the example I started with, at least in our view, communication optimal rules seem more in line with empirical practice. Right? In particular, we're not aware of any unemployment audit studies that just report out the sorted data, although many do report the unsorted data. And there are some studies in the literature that actually report both. So they report both the raw estimates, and then they sort the estimates to get this monotonicity. That said, coming back to the discussion we were having with Greg earlier, it's not always practical to just report the raw data X. And so the next question we want to think about is, can we find some practical ways for analysts to reduce communication risk in such settings? So to think about that question, let's think about a case where we're interested in some scalar parameter tau. right? So tau could be some causal effect of interest, or a counterfactual, or a causal effect, or an optimal policy, or whatever. Right, and for example, you might think of the loss just being the squared estimation error for tau theta. When we're interested in such scalar quantities, right, empirical research might report an estimate tau hat for tau, along with some set of other statistics S hat, right, where these statistics could be descriptive or summary statistics about the data, placebo or falsification tests, sort of trying to say, if I construct a version of the data set where something goes wrong, what happens to my analysis, or other sorts of auxiliary statistics trying to make the estimate tau hat more interpretable. And in some of our other work, we discuss each of these through the lens of communication risk, but for today, let's focus on this last category, auxiliary statistics. So one very common sort of discussion to see in empirical work, at least in economics, is some sort of attempt to summarize what's driving the conclusion of a given analysis, right? Where often this is accomplished via some sort of informal discussion about what's leading the sort of estimation exercise to find the conclusions that it's finding. And one formalization for this, to try to capture what's driving the analysis, is to just ask how the estimate tau hat changes in the underlying data X. Right, where for small changes in X, that's going to be captured by the sensitivity, so just the derivative of our estimate with respect to changes in the data. Right, reporting such a sensitivity measure is especially natural in settings where X is low dimensional. Right, so imagine that I'm estimating some quantity of interest by basically matching a vector of model predictions to a vector of summary statistics for the observed data. Right? One thing that's natural to do in such a setting is just to ask, how does my estimate change if I wiggle the first summary statistic, the second summary statistic, and so on. Right? And we show that in such low dimensional settings, you can construct an asymptotically valid estimate for this sensitivity as a byproduct of the usual standard error calculations that folks are already doing. And so in that sense, it's sort of an estimate for this is available at almost no additional computational cost.
Well, to clarify, this sounds like something that's a property of the model, not property of the data.
Yes. Well, and so it's both, right? Because in some sense, this derivative is going to change depending on which point X I evaluate it at. But yeah, exactly. This is a property of both the model and the data.
No, but wait, you can, it sounds like the derivative is what you push out. So the user evaluates it at any points they want.
Sorry, so we're thinking about something similar to report here, which is just the derivative at the realized data point.
At that one point, got it, okay.
At that one point, exactly, yeah. And linking this to the earlier results, right, we show that in that communication formalism, right, reporting sort of this simple additional statistic, which is just the derivative of the estimate at the particular realized data point, can improve communication because we show a sense in which it can make the reported estimate more interpretable for audience members concerned about the modeling assumptions. To illustrate this, we looked at a number of applications. Here I'll just talk about one looking at charitable giving. So the paper here on testing for altruism and social pressure in charitable giving was interested in the question of what are the welfare effects of charitable solicitations. Right, and the basic trade-off you can think of here is, on the one hand, right, someone asking me for money for charity gives me the opportunity to contribute, right, and maybe I value the cause, so I value giving money. On the other hand, maybe when someone asks me for money, I feel uncomfortable, I feel some kind of social pressure, and so in that sense, it's utility decreasing. So to tease this out, the authors conducted an experiment where they randomized across 3 treatments, right? A no-flyer treatment where a solicitor just showed up at a household's door. A flyer treatment where a flyer was left a day in advance at the household, telling them that the solicitor, or I forget if it was a day in advance, was left in advance at the household, telling them that the solicitor was going to be coming, right, and when. Yes, day in advance. And then the third treatment, the opt-out treatment, where a flyer was left and households were given the option to check a box if they didn't want to be disturbed. To sort of connect the results of this experiment to the motivating question, right? The authors modeled the data here as the result of a 2-period game between the solicitor and the household, where households have utility from giving, right? So they might like giving money to these charities, but disutility from social pressure. right, where the social pressure is indexed by a parameter tau. And the particular functional form they assume is that social pressure decreases linearly in the donation amount until a threshold, right? So the amount of discomfort I have from not giving money decreases linearly in the amount I give until it hits the median donation amount of $10, and then it's flat. So to estimate this model, right, they match the observed shares of folks opening the door, opting out, and donating various amounts under the different treatment arms, right? And so those shares are going to be the underlying data X in this example. And the question here is, what features of X drive their social pressure estimates? Now, the authors provided some informal motivation for this, some informal discussion of this point in their paper, where they said that the social pressure was identified from two main sources of variation, right? Home presence in the flyer treatment and the distribution of small giving. In particular, the higher the social pressure, the more likely is small giving, and in particular, bunching at this donation threshold of $10. So to look quantitatively at this, right here, we're reporting that sensitivity measure I showed you earlier for their social pressure parameter estimate, tau hat, in this particular application. So on the vertical axis, right, I've got the different elements of X, right? So for example, the fraction of folks opening the door under the flyer treatment, under the no flyer treatment, under the opt-out treatment, the fraction of folks opting out when given the option to do so, and so on. On the horizontal axis, I'm showing you the absolute sensitivity, where the signs are given in parentheses here. Right, the blue dots are the moments that the authors highlighted in their verbal discussion. Right, we see that indeed, the sort of fraction of folks giving $10 is playing a really, really big role in driving the conclusions of this analysis, in sort of driving the social pressure estimate tau hat. Why would this be potentially useful if you were skeptical of their model? Well, if I'm not certain about this model that says social pressure decreases linearly until it hits $10 and then it stops, right? This tells me that as a byproduct of that model, the fraction of folks giving $10 is really, really important here. So maybe that's something I might be nervous about. Now, reporting that sort of a sensitivity measure is nice in some cases, but there are a lot of cases where that's going to be hard to report or interpret. For instance, right, think of an estimation procedure where the data enter observation by observation rather than just through summary statistics. Right, that'll be true of many cases, but for instance, will be true of maximum likelihood estimation in many settings. In that case, right, this derivative is going to be a vector of same length as the data set, which might not be very appealing to report or interpret. So in some of our more recent work, we show how to adapt our approach to this sort of setting, where the basic idea is to try to exploit the asymptotic relationship between these estimates tau hat and the sorts of intuitive descriptive statistics that researchers often discuss, at least informally, in economics applications. And we again apply this in a number of settings. So with that, let me wrap up, and then happy to open the floor to discussion. So to summarize, right, today I've argued that focusing on communication rather than decision making can really change our understanding of the goals of an empirical scientist. In particular, right, if we put the focus on communication, it emphasizes allowing the audience to make informed judgments rather than trying to pick sort of a single best decision or estimator for everyone. Right, and as a consequence, it suggests some practical improvements for improving transparency of empirical research in some common settings, at least in economics. So thank you all very much, and thanks so much for the questions.
Well, thank you very much. Any questions from anybody online? Well, then I will ask you, let me see, so this stuff makes sense, but I would like to maybe come back to what I was talking to Jesse about before, because this is still kind of this hot topic in my mind, which is a lot of this work is estimating parameters of notably different models for different people, and all these models are wrong in some creative ways. What's the value of estimating parameters and communicating? Am I really trying to nail down what is this value?
Yeah, and so I think the perspective that I would take, and I suspect Jesse shares, but let me speak for myself. I think a lot goes into how we define tau, right? And so I think the way that I would think about this is in a lot of settings, right? I think we can define quantities of interest tau, which under the model are functions of the model parameters, but have a model-free existence, right? So for example, right, maybe my question is, how should we be setting, regulatory policy in industry A, right? And we're thinking about, regulatory policies 1, 2, or 3. So you could imagine, right, just defining, what are economic outcomes going to be under policy 1? What are economic outcomes going to be under policy 2? What are economic outcomes going to be under policy 3? Right, and those are sort of objects which I fundamentally don't know, but they have a model-free existence. Right, in some sense, I can say, well, there would be some outcome if I implemented this policy, but I don't know what it is. Now, under the model, I can write tau as a function of theta. Right, I can say, well, if I embrace this particular model, then outcome under policy 1, outcome under policy 2, outcome under policy 3 are functions of theta, and we can calculate them if we knew theta, and so on. But I think the way I would sort of set things up is to say, let's define some quantity of interest in a model-free way, which has, an independent existence, and then we can think about the question of, how useful is a given model, or the estimates, how useful are the estimates coming out of a given model for informing me about that quantity of interest if I don't believe the model, versus, what things could the researcher estimating the model report that would make those quantities more useful for me, learning about the quantity of interest and so on. And so in that sense, go ahead.
Well, that's if I really trust my model, which in this case I do not, because or that parameter like happiness or look, that's a nasty one, right? But ultimately we try to optimize, right?
Yeah, so happiness is hard, but I think that's right, so imagine, let's take like a really simple, right, imagine that just my goal is to, maximize, let's take a labor example. My goal is to, maximize the lifetime discounted earnings from students attending a particular school district, right? Now, if I have a model, right, that sort of, my model will make predictions for what those earnings will be under different states of the world. But I guess the way I would say it is, even if I sort of don't believe in any particular model, right, it can still ask, under what I do believe, right, which is like, this model is kind of off, that model is kind of off, this other model is kind of off. Learning the outputs of those models are still potentially going to be correlated with the thing that I want under my prior, right? So they don't give me exactly the thing I want, right? But if, all the models agree that, the outcome is super high, that probably moves my beliefs about the truth up, even though I think none of the models is exactly right.
Sort of. It's when it's not too contentious, yes. But when you have models which are, Republican, Democrat, those are the best kind of divergence in America today, right? All the important things, their models completely diverge. So in that case, I have, if it's a prediction exercise, I have something about the model for which there's an experiment. Also, I have an error function. But if it's an unmeasured thing for which I only have words, and I hope that the parameter even matches my words, what do I do with that? It's universal, right?
But so I think, a couple thoughts, right? So one thing that actually we have some examples sort of illustrating points where there are sort of cases, there are interesting cases with different, there are important types of, there are useful distinctions that, at least for us, sort of came out of some of this analysis between disagreement and uncertainty. Right, for example, right, to just take like a toy example, right? Imagine that there's some model being estimated, and we all think that model is wrong, but each of us has a dogmatic belief about how the model is wrong, right? So I believe its estimate is biased upward by 5 units. You believe its estimate is biased downward by 50 units, and so on. Right, so sort of, we all think it's wrong. We all disagree about the way it's wrong, but we're all certain in our belief. Well, in that case, actually learning the estimate from that model is actually really useful to all of us, because I get the estimate and I correct it in one direction by 5. You get the estimate and you correct it in the other direction by 50. And so that's a case where we all strongly, strongly disagree with the model, and we strongly, strongly disagree with each other. But there is something that the analyst can report which is useful to all of us. Right, and I would distinguish that from a case where we're all very uncertain about how the model is wrong. Right, I think it could be biased upwards or could be biased downwards, and I don't know. Right, and so I think that's one distinction for this sort of setting that I think, at least for us, has turned out to be useful, is basically that there are important distinctions between sort of disagreement and uncertainty. And in the presence of strong disagreement, there may still be very useful things to communicate.
All right, so well, if you are if you're disagreeing so much, how can you possibly be agreeing on what that parameter really means enough to adjust in such a reliable way?
Yeah, right. Well, so right. I mean, all examples are necessarily somewhat stylized,
yeah.
But I think, we could, right. So take like the lifetime earnings example, right? I think we all agree, sort of. I think we could all agree on what discounted life, right? If we just say, I'm going to use a 5% discount rate. Here's present value of discounted lifetime earnings.
Yeah, I think in that case, we can agree on if privacy was not an issue, how you would measure it. We can agree on that, thankfully.
Exactly. Yeah, and imagine we're working with an analyst who has access to the IRS tax records. Good. And so they can't tell us what these things, they can tell us some aggregated version of this thing, and so we're not worried on that level. And so in that case, sort of, we all agree what the parameter is, but we might really, really disagree, right, about the effects of different policies are going to have on the parameter, or we might really, really disagree about, there's some estimation strategy a researcher is using, and we really disagree about whether that estimation strategy is going to do any good at recovering the parameter. And some of us think that estimation strategy is going to be really biased upwards, and some of us think that estimation strategy is going to be really biased downwards. Mm-hmm. Right. That basically the sort of example I was going to before is basically to say, in that setting, if each of us is like pretty confident in our belief about what the bias of that estimation strategy is, so like I'm pretty sure this thing is going to be biased upwards by like $20,000, and you're pretty sure it's going to be biased downwards by $100,000 or whatever, mm-hmm. Right? Then actually, that's a case in which it's actually quite useful for us to know what that estimate was, right? Because even though sort of all of us think it's a bad estimate and we disagree about why it's a bad estimate, all of us also think that we know how to fix it, right? And so if you tell it to us, we all will update our beliefs in light of that information, even though we really, really disagree about sort of what the takeaway is from the information.
Right. No, it helps a lot, because in this case, we don't worry about understanding the world. We do have a common conception of the world, thankfully. It is a matter of communication risk. And I guess where I'm driving to, which, nobody knows how to do, so it's all good, is there is a crazy world out there, and we're really confused about it. Like when I'm thinking basic laws of motion, when you start going through them, they make no sense compared to our everyday experience. But after a couple hundred years, people figured them out after a bunch of trial and error, and even they had to be revised. So it's like, how do you do that consistently? And economics is much, much worse.
Yeah. I think so. Partly how we have tried to deal with this, deal with some related issues to this, is by avoiding, because there are tons and tons of things we could define as the object of interest that only have a meaning within a particular model. Mm-hmm. And then it's sort of like, what does it mean to try to estimate that thing when the model is wrong, because I don't know what that quantity is. And so I think that's actually part of why I think for many of our preferred examples are exactly to sort of try to sidestep that issue and define the object of interest as something that kind of has a model-free meaning.
That's very helpful. It simplifies the attack at the problem.
Well, just because otherwise I have no idea. Yeah. It seems hopeless.
All right. Awesome. Well, yeah. Thank you. Looks like we're at time. But thank you very much.
No, thanks for having us. This was a super interesting discussion. Thank you very much.